Welcome to Understand Chemistry. I am Dr. Bilal, and today we are diving into another fascinating topic in polymer chemistry, copolymers. In this video, I will walk you through what copolymers are, explore their different structural types, and guide you step by step through the derivation of the Mayo-Lewis equation, which is a key tool for predicting copolymer composition. Let's get started. Let's begin by understanding the basic difference between homopolymers and copolymers. Homopolymers are made from a single type of monomer repeated throughout the chain. For example, polyvinyl chloride, polymethyl methacrylate, polyvinyl acetate, and polystyrene. All of these are built from just one type of repeating unit. Their properties are often predictable and uniform. Copolymers, on the other hand, are formed by combining two or more different monomers in the same chain. For example, styrene-butadiene copolymer (SBR), which is formed by copolymerization of styrene and butadiene. Similarly, styrene acrylonitrile copolymer is obtained as a result of copolymerization of styrene and acrylonitrile. Now let's explore why copolymerization actually matters. Why we need copolymers. Copolymers allow us to combine the strength of different homopolymers. This means we can design materials that are more versatile, more durable, and more application specific than what we had from a single monomer alone. Take polystyrene for example. It is a homopolymer with a high rigidity and good processability. It has a thermoplastic behavior which is useful, but it is also brittle, has only moderate solvent resistance and limited toughness. These limitations restricts its use. Now, if we copolymerize styrene with 1,3-butadiene, or generally we say butadiene, we get SBR, styrene-butadiene rubber. This material is far more elastic and impact resistant. That's why its use in tires, seals, and footwears. These are the products where flexibility and durability are critical. In another approach, if we copolymerize styrene with acrylonitrile, we get styrene acrylonitrile copolymer. This copolymer is stronger and more ductile than polystyrene, and it offers improved resistance to aliphatic hydrocarbons and mineral oils. That makes it ideal for outer casing of devices and kitchen appliances. So you can see how copolymerization expands the performance range of materials. By choosing the right comonomer, we can fine-tune mechanical strength, chemical resistance, flexibility, and even thermal behavior. Now, let us look at the different structural types of copolymer, which are defined by how the monomers units are arranged along the polymer chain. First, we have alternating copolymer, where monomer A and B repeats in strict AB-AB pattern. This regularity often leads to predictable properties and crystallinity. Next are statistical copolymer, also called random copolymer. Here A and B units are distributed randomly. Then we have block copolymer, which contain long segment of A units followed by long segment of B units. Finally, graft copolymers, where we have polymer backbone consisting of long polymer chain of one type of monomer with side chain of another type of monomer grafted onto it. This architecture is useful for modifying surface properties. We will go further deep in understanding each copolymer type later. But for this moment, let us understand the nomenclature of copolymer. In very general context, regardless of particular type of copolymer, a copolymer made of monomer A and B can be written as poly A co B, where co is written as italic. But when we are too specific for a particular type of copolymer, then we can use specific nomenclature. For example, for alternating copolymer, we write poly A alt B. For statistical copolymer, we write poly A start B. For block copolymer, we write poly A block B. Similarly, for graft copolymer, we can write poly A graft B. Please do remember all these short forms for each particular type of copolymer like alt, start, block and graft must be written in italic. Let us understand the nomenclature with the help of example. Here is the structure of styrene-butadiene copolymer. Since it is copolymer, we can write polystyrene co-butadiene. But if we bother which particular type this copolymer belongs to, then we can write polystyrene start butadiene as it is a statistical copolymer. Let us take another example of styrene-methyl methacrylate copolymer. For this, we can write polystyrene co-methyl methacrylate, or more precisely, polystyrene ren-methyl methacrylate. Ren is for random copolymer. This is interesting. In the last example, where monomers are random, we say statistical copolymer, but in this example, we are saying a random copolymer. So let us understand the difference between random and statistical copolymer. Random copolymers have an irregular monomer sequence. There is no predictable pattern, means the arrangement of A and B units is purely random. This happens when both monomers have similar reactivity. So the growing chain does not favor one over the other. A good example is polystyrene ren-methyl methacrylate, where styrene and methyl methacrylate are incorporated without any bias. On the other hand, statistical copolymer looks random, but it follows predictable statistical rules. This sequence depends on the reactivity ratios of the monomer and the feed composition. That means if one monomer reacts faster, it will appear more frequently in the chain. For example, in polystyrene start butadiene with a feed of 23% styrene and 77% butadiene, and with known reactivity ratios, we can statistically estimate the average spacing. For instance, how many butadiene units typically occur before a styrene units appear. Now let's look at what's happening at the molecular level during the radical copolymerization. We are dealing with the two monomers here, M1 and M2, and the process begins when the radical species initiate chain growth. If the growing chain ends in M1, it can react with either another M1 or other M2. When it reacts with M1, the new chain will end in M1. The rate constant of the reaction is shown by K11, and when growing M1 chain react with M2, the new chain ends in M2. The rate constant for this reaction will be K12. Similarly, for all the growing chains ends in M2 have two possibilities. Either it reacts with M1 with rate constant K21 to give chain that ends with M1, or it combines with M2 with rate constant K22 to give chain that ends with M2. The rate of reaction for each type of reaction is shown here. The rate of any reaction is the rate constant multiplied by the product of concentration of reacting species. In order to find at what rate both monomers M1 and M2 are being consumed, let us consider the disappearance of M1, which is the negative rate of change in concentration of M1, equal to the sum of rate of reactions that involve M1. These are these two reactions highlighted in red. Let us name this equation as alpha. Similarly, for disappearance of monomer M2, we can write negative rate of change in concentration of monomer M2. That would be the sum of reaction rate that involve M2. These are highlighted in blue. Let us name this equation as beta. Now, in order to find the ratio of disappearance of monomers M1 over M2, let us divide equation alpha by equation beta. We get this equation. Taking M1 and M2 from numerator and denominator respectively, we reach to the equation gamma. Now, to simplify the system, we assume a steady state condition, meaning the number of growing chain remain constant throughout the reaction. This means the rate of conversion of M1 ended chain to M2 ended chain is equal to the rate of conversion of M2 ended chain to M1 ended chain. That is, the rate R12 is equal to the rate R21. By substituting the values and solving for concentration of chains ended in M1, we reach to this equation. Now, let us substitute this value of concentration of M1 ended chain into the equation gamma. We get this equation. In this equation, let us separate the common factor, and after cancellation, we get this equation. For further simplification, let us divide each term by K21, and after cancellation, we reach to this equation. For further simplification, we can introduce copolymerization parameter R1 and R2. These are defined as ratio of rate constants. These are also called reactivity ratio of monomers. It tells us how strongly a propagating radical prefers to add its own monomer versus the other monomer during polymerization. I will discuss later the possible cases arises due to different values of reactivity parameters. By substituting copolymerization parameter into the last equation, taking LCM in the numerator and denominator, and after cancellation we are ended up with this equation. This equation is called Mayo-Lewis equation. In this equation, the small m1 and m2 stands for the concentration of monomer M1 and M2 in newly formed polymer. The concentration of M1 and M2 square brackets indicate the concentration of monomers in the reaction mixture, and R1 and R2 are copolymerization parameter. Let us discuss some of the key implications of Mayo-Lewis equation. Mayo-Lewis equation gives us a practical tool for predicting copolymer composition at any point in the reaction. One of the most important takeaway is that copolymer composition involves with conversion. That is, as polymerization proceeds, the relative consumption of monomer changes, especially when their reactivity ratios differ. One monomer may be consumed faster than the other. This leads us into the concept of time-dependent polymer chemistry. Unlike small molecules, polymers formed at different stages of the reaction are not identical. Early chain may contain more monomer A, while later chain may contain more monomer B. Now, under low conversion condition, typically below 5%, the monomer concentration remains nearly constant. In this regime, the Mayo-Lewis equation provides a reliable estimate of copolymer composition with minimal error. But what happens at complete conversion? When all monomers are consumed, the average composition of the entire polymer batch reflects the initial monomer feed ratio. In fact, chemical heterogeneity at full conversion becomes a key concern because chains were formed at different times under different feed composition. The final polymer is a mixture. Some chains are rich in A and others are rich in B, and some may lie somewhere in between. This heterogeneity can influence mechanical properties, phase behavior, and even processing performance, which brings us to practical implication for material design. If your goal is to produce a copolymer with specific composition or uniform properties, you must control both the feed strategy and the extent of conversion. Hope you understand the concept of copolymerization. Thanks for watching.